Linear combination, the act of multiplying vectors by scalars and then adding the results together, that's the operation that is the engine of linear algebra, because it's what makes vector spaces vector spaces. Vectors can be said to be anything that we can do linear combination to, anything that we can scalar multiply and add to one another for appropriate definitions of scalar multiplication and addition. And so in this section, we want to start speaking the language of linear combination and figure out how to relate it back to what we already know how to do, which is to set up and solve systems of simultaneous linear equations. So in this section, we start out with just the definition again of what linear combination means. A linear combination of a set of vectors, so you give me a set of vectors v1 up through vm. A linear combination is the result of taking a group of scalars, c1 up through cm, so these are just real numbers if that's the base field of our vector space, multiplying those vectors by those scalars, so c1 times the first vector plus c2 times the second vector and cm times the mth vector, and then adding all those results together. So the example that's here I think helps to clarify that there is a linear combination of the vector 1, negative 1, 2 and the vector 1, 2, 1 that adds up to the vector 3, 0, 5. And specifically, that linear combination is 2 times the first vector added to 1 times the second vector is going to give me 3, 0, 5. So 3, 0, 5 is one of the linear combinations of the vectors 1, minus 1, 2 and 1, 2, 1. There are a whole bunch of other linear combinations as well, because we could have picked any scalars here to multiply those vectors by. It just so happens that picking 2 and 1 as my scalars gives me the linear combination that equals 3, 0, 5. But of course we have infinitely many choices to make here. And so infinitely many linear combinations are possible for a given set of vectors over an infinite field, like the real numbers. And so that leads us to the second definition. The span of a set of vectors is the collection of all possible linear combinations that we could pick. So if you give me the two vectors 1, minus 1, 2 and 1, 2, 1, the ones we looked at in the previous slide, the span of that set of two vectors is another set of vectors that consists of every possible linear combination of 1, minus 1, 2 and 1, 2, 1. It's the set of every scalar multiple, a times 1, minus 1, 2, added to every scalar multiple of 1, 2, 1, where the scalars that we select can be any real numbers. So any scalars from the field over which we have a vector space. And so if I have m different vectors, and I take the span of all m of those vectors, that's going to give me the set of all linear combinations of those m vectors. So I can pick from any real number for each of the m different scalars as a part of this. So typically, it's the case that if you give me a set of vectors that only includes like 1 or 2 or 3 vectors in it, typically the span of that set of vectors is going to be some massively large infinite set. And it becomes infinite just because we end up with infinitely many choices for the scalars that we're multiplying those vectors by before we add them. So the activities that you're going to do in this section begin by just trying to characterize what does the span look like? What is the set of all linear combinations of a set of vectors in some simple cases that are not too challenging to visualize? And I have a couple of Desmos tools for you to help you with the visuals in this process. So if we want to consider what is the span of the vector 1, 2 in the xy plane, we're asking what does the set of all linear combinations of 1, 2 look like? But since there's only one vector in my set, I can do scalar multiplication, but I'm not doing any addition as part of my linear combination. I'm just getting scalar multiples of that vector. And so in the Desmos worksheet, for example, we'll be able to see that this set, the span, is going to contain 1 times the vector. It's also going to contain 2 times the vector. It's going to contain 4 times the vector. It's going to contain 3 times the vector. It's going to contain 2.3 times the vector. It's going to contain 0.56 times the vector. It's also going to contain negative 1 times the vector. It's going to contain negative 4 times the vector, and so on and so forth. So when we say the span of the vector 1, 2, what I mean is every single one of the purple locations, the purple points, the purple vectors inside of the xy plane that can be reached via a scalar multiple of the vector 1, 2. And so in the first activity, that's going to be your job to try and describe that as a set of vectors in the xy plane. And so that's going to give us a sense of what the span of a single element set, a single vector, might look like. Where things get a little more interesting is if we have more vectors in the set of which we are describing the span. And so in the second activity, you have 1, 2, and minus 1, 1. And we want to try to come up with a representation of what the set of all linear combinations of those two vectors might look like. That's what we call the span of those two vectors. So the set of all vectors that we can write as a scalar multiple of 1, 2, added to a potentially other scalar multiple of minus 1, 1. So in the xy plane, what we're looking like here is, here's 1, 2, here's negative 1, 1. I can pick whatever scalar multiple of each one of those vectors that I like, but then I'm going to add those scalar multiples together, and the result is going to be one of the points like the point up here in blue. So the question here is, how do I describe, as a subset of xy space, as a subset of R2, all of the possible locations that I can reach, all the possible blue points, everywhere that the blue point can go, by taking a scalar multiple of one of my vectors and a scalar multiple of the other of my vectors and adding those scalar multiples together. Where can this blue point go? Is there any place that we can't reach through this process of taking a scalar multiple of one of these vectors and adding it to a scalar multiple of the other? And so you'll describe what that span of two vectors in R2 looks like in the second activity. Then we ramp it up to the third dimension in the third activity. Well, actually, that comes in the fourth activity, I think. We'll just do this activity again, but with a pair of different vectors, 6, negative 4, and negative 3, 2. The Desmos activity that I've linked for activity number 2, you can go in and modify it just by changing the coordinates, or actually you could just drag these vectors around if you like, so that you can have the coordinates that you're looking for the third activity for today. And the fourth activity, we ramp it up to the third dimension and say, well, what might spans of two vectors inside 3 space look like? Where can we get to in 3 dimensions by adding some multiple of 1, 0, negative 3 to some multiple of negative 1, negative 3, 2? And the key thing, and this is why this activity is a real culmination of everything we've learned this semester up until this point, we want to understand how the question, what is the span of this set of vectors, is related to the question, what are the solutions of a particular linear system of equations? So this is the big trying to make a connection part, right? Because the set of all linear combinations of two vectors is the set of everything that we can get by multiplying one of those vectors by an unknown and the other vector by an unknown and adding the results. And if I want to know whether another vector belongs to that span, I'm asking, is there a solution to the vector equation? Constant times one vector plus constant times another vector equals the third vector. And so reinterpreting this question as a system of equations question enfranchises all the tools that we learned in the first chapter that can help us to solve such a system. And so 2.2.4 is really about bringing that point home. And the picture in 3 dimensions, just as in the picture in 2 dimensions, looks the same. The question we're asking here is it possible for me to take a scalar multiple of one vector, my v vector that's right here, and a scalar multiple of my other vector, my w vector, and add those scalar multiples together? And when I add those scalar multiples together, the result, which is the black vector on here, is exactly equal to the 1, negative 6, 1 that we're trying to get to. So is it ever possible for me to exactly hit that blue point with some linear combination of the two vectors that we started with? And if it is possible to do that, then this vector equation up here must have a solution, right? There must be an x1 and an x2. There must be a linear combination of these two vectors that produce the third vector. And if it's consistent, if there's a solution, that means that this vector must belong to the span. But if there's no solution, that means that this vector does not belong to the span. So that activity is the goal to get to today. That if you get to 2.2.4 and really feel like you understand it, then you are in great shape as we wrap up today's material.